This is AP Precalculus. We're on the notes for topic 1.5, polynomial functions and complex zeros. There's a lot of material for this lesson compared to other lessons. Let's dive in. So we've got a definition of zeros of a polynomial. So given a polynomial function, and we're just saying the polynomial function is p of x, if we plug in a and get 0, then a is known as a 0, or it's also called a root of p of x, and that is also known as an x-intercept. So all of these are kind of synonymous. You can say that a 0, a root, an x-intercept, they all kind of mean the same thing. So, and it also goes further and says, hey, let's go ahead and say if a is a real number, then x equals a is the 0. So when it comes down here and we say, okay, find the real zeros, what we're trying to do here is we're trying to find what x is equal to, solve for x. And it also says that x minus a is a linear factor of p, and that kind of doesn't make sense, right? Where does this minus a come from? And here's the answer. If I'm setting this thing equal to 0 to find a 0, then I'm saying x minus a is equal to 0, and I can add a to both sides, and x is equal to a, which is exactly what we have over here. So just remember that in order to find the actual answer for our zeros happen, when we're only given linear factors, we need to kind of do the opposite of whatever's on the inside, or at least solve this thing by setting it equal to 0. Most of the time, you're going to have a simple x, but you have something else like a 2x or an x squared, then you do need to set this thing equal to 0 and then solve. All right, so I want to talk about repeated zeros, which is also known as multiplicity. I want to give you a synonym of multiplicity. Another name of multiplicity is power. And another synonym for that is exponent. Anytime that you see an exponent on that linear term, that's just the multiplicity. So generally speaking, you're only looking at linear factors, and they can be repeated n times. Then that corresponding 0, this value over here, has a multiplicity of n. So far, so good. Typically, we know that the graph of polynomial passes through the zeros on the graph. So I'll say this is through the zeros on the graph. However, when a 0 has a multiplicity greater than 1, the graph will behave differently near the 0. If I have a multiplicity of 2, 3, 4, I have a power of 2, 3, 4, something weird will happen. Okay, so check it out. I have this function, and it's graphed over here. And we're trying to look at the behavior around the zeros of the function. So check it out. When I set this x plus 4 equal to 0, if I say that x plus 4 is equal to 0, then I'm going to subtract 4, and I get x is equal to negative 4, which means the x-intercept happens at x equals negative 4. If I come back down here to this graph, you can see down here at negative 4, I passed through the graph, and that came from this linear factor, x plus 4. Okay, I'm going to erase that because I just wanted to show where that came from. That means that this x plus 1 term has an x-intercept of negative 1, and we can see right here it passes through. And at x minus 3 is equal to 0, I'm going to add 3 to both sides, etc., and this is going to turn into a positive 3 x-intercept over here. Notice that we went through the x-axis, but then we turned around at the x-axis. Why? Why did that happen? And I want to be a little bit more thorough than the notes already are and maybe go in a little bit too in-depth, but this will help us in the long run, I feel. Whenever you have odd powers, odd multiplicities, technically this was a power of 1 right here, notice what happens. This 1 went through the graph, this 3 went through the graph, but this 2 turned around. Most people from this can determine the correct rule, which is this. If you have an odd multiplicity, then you go through the graph. My U's look better. You go through, not through, through the graph. And if you have an even multiplicity, you turn around at those x-intercepts. So what I'm also trying to tell you is this. The multiplicity of the 0 is the power, or the exponent, or the, what is another term for that? You can say that it's the degree. All of these mean the same thing, so I'm just going to write them all here. It's the degree, it's the power, it's the exponent of its factor. And I've already kind of said that up here, that multiplicity and exponent are All right, someone's trying to call me. At x equals 3, oh wait, so I haven't read this all yet. We can include that the multiplicity when we list the zeros. So this is how we usually write that. We say x equals -4, which we already knew, and that has no multiplicity, so we don't write anything. You assume that the multiplicity is 1 when we don't write anything. At x equals -1, that is another x-intercept at -1. That had a multiplicity of 3. Why? Because this was a power of 3. This one was a power of 1, so we didn't write anything. And x equals 3 had a multiplicity of 2 because we said we had a power of 2. All right, so at x equals 3, we have a multiplicity of 2. Yep, we just said so right there. The graph of the polynomial is tangent to the x-axis. So the graph, check it out, the slope is positive, and then eventually the slope comes down. The slope at 3 has this slope that is 0, which means that we are tangent to this, or parallel to this x-axis. So it bounces off the x-axis, yes, and we have this tangent line, which is tangent to the x-axis whenever we have even. So that's a rule that you can determine just from knowing this, that whenever you have an even multiplicity, we turn around. If we turn around, we have to have a slope of 0. So we have a tangent to the x-axis. This is a very fancy way of saying that the slope is equal to 0. All right. In example 1, for each of the following polynomials, determine the degree of the polynomial. So that's step 1. Find all zeros as step 2, and then state the multiplicity of each zero. And let's try writing it like they do up here. If we assume that the multiplicity is 1, I guess we can just write multiplicity of 1. Okay, so it's super important for each of these functions to make sure that they are completely factored. A is completely factored, but B and C can be factored even more. So in A, it's already factored, so we can just go and jump into the degree. So in order to find the degree, I want to do this in pen. The degree can be found by multiplying the highest powers. So this hasn't been multiplied out. This +1 is not going to increase the power. This -4 is not going to increase the power as much as just this x and this x will. I'm eventually going to multiply, again, that -2 doesn't really matter that much. I care about the power of x's. This x is to the power of 3, which will be multiplied by this x, which is to a power of 1. And those two will be multiplied by this x, which was technically to a power of 2. So I'm going to multiply all 3 of those x's together. And when I multiply the same base, I add their exponent. So I'm essentially adding 3 plus 1 plus 2, which adds up to 6. The degree here will be 6. And you can multiply this all out, but it's way too much work to figure what that is all the way. So the degree is 6. We just add up their powers. And then from there, we're going to find next, what is it asking us to do? Find all the zeros. So to find the zeros, what we do is we set each of these terms equal to 0. So let's do the first one. If I set I want to do this in pen. If I set -2x to the power of 3 equal to 0, I'm going to divide both sides by -2, and I get x to the power of 3 is equal to 0. If I cube root both sides, I get x is equal to 0, which is our first 0. Okay, let's do our next one. If I set x plus 1 and set this one equal to 0, again, I'm setting this linear factor equal to 0. Then I'm just going to subtract 1 on both sides, and I'm going to get x is equal to -1. And finally, I'm going to have x minus 4 quantity squared is set equal to 0. And I'm going to square root both sides, which will cancel out that square, and I'm left with x minus 4 is equal to 0. And from there, I can add 4 to both sides, and x is equal to 4. So these are all of the zeros. I have a 0, a -1, and a 4. What are the multiplicities of each of these zeros? We have to look at the power that it originally was. So this one came from a 2x to the power of 3. That had a power of 3, so this multiplicity, all right, multiplicity is 3. This multiplicity up here came from this power right here, and that power is hidden, but it's technically a 1, so that multiplicity is 1. And this multiplicity for this 4 came from this power up here, this power here, which is a multiplicity of 2. Again, it's just really the power that that linear factor was raised to. All right, in B, again, I need to first find the degree. So if I multiply everything by 3, it's not going to change the degree, so I can kind of ignore that. I'm going to have this x is going to be to the power of 4 eventually, so this is really x to the power of 4, and this is x to the power of 2. This -4 and this -2 will not make us have any higher power. The highest powers, if I multiply them, is the quicker way to go. So x to the power of 4 times x to the power of 2, we add the 2 and the 4, we get 6. This is a degree 6 polynomial. Okay, let's find the zeros now. To find the zeros, Ooh, I'm noticing that I already said this before, but this can be factored more. This x minus 2 is completely factored because it's a linear factor. If this is x to the power of 1, it's probably as far as you can go. This is an x to the power of 2, which means we can probably factor it further, but maybe not. So there's one thing that I can do, and I can see that this is a square. This is technically x squared, and this is also a square. This is technically 2 squared, and there's a minus sign in between 2 squares. This is what's known in the business as a difference of 2 squares. A difference of 2 squares can always be factored as a conjugate pair, which means this can really be rewritten as 3 times the quantity of x minus 2 times x plus 2. So again, I just rewrote x squared minus 4 as x minus 2 and x plus 2, and I still need to rewrite this x minus 2 to the power of 4 up here. This is x minus 2 to the power of 4. This hasn't been fully factored yet. Now it's been factored a little bit more, but check it out. Look at all the copies of this linear factor x minus 2. I have x minus 2 right here and another x minus 2 right here. I have 1 copy here and 4 copies here for a total of how many copies? And I ran out of room, so I'm going to move these down a little bit. And I'll say that this is a total of, there's 3 times x minus 2. How many copies? There's 5 of those copies times x plus 2. And there's a total of 1 of those copies. You don't really write the 1, but I'm going to write it because it might help us later. So to find the zeros, I'm going to set this term equal to 0. I'm going to set x minus 2 to the power of 5 equal to 0. I'm going to take it to the 5th root of both sides, and I'm going to just get x minus 2 is equal to 0. And then I'm going to add 2 to both sides to get x is equal to 2. I'm going to set x plus 2, this is to the power of 1, so I'm just going to say set that equal to 0. If I subtract 2 on both sides, I get x equals negative 2. These are the two zeros, at x equals 2 and x equals negative 2. Then I'm going to find their multiplicities. The multiplicity of 2 came from this power of 5. So this multiplicity is 5. And over here, this negative 2 came from this x plus 2, which had a power of 1. So the multiplicity over here is a multiplicity of 1. This 5 can be rewritten to make it look a little bit nicer. And then finally, we have part C. Both of these are not even factored. So the first thing that I see on this term is that it's a cubic, and I'm worried about how I have to do a cubic. Usually you have to do something complex, but check it out. All of these have an x, which means we can just factor out a greatest common factor. The greatest common factor here is x, and what's left over is dividing each of these terms by x. They all kind of go down a power. Instead of it being a power of 3, it's a power of 2, minus x to the power of, it used to be a power of 2, and now it's a power of 1, so just minus x, and minus 6, because I divide this by x, and the x's cross cancel. All right, and I'm just going to rewrite this for now. This is going to be x squared minus 7x plus 12. Both of these greatest common factors, there was no greatest common factor here. The greatest common factor over here was factored out. Now I'm going to do more factoring. In my class, we use a ninja star, which is a fancy way of saying, hey, what 2 terms add up to the middle term, the middle coefficient, which is negative 1, and multiply to negative 6. And multiply to negative 6. So what multiplies to negative 6? Well, 1 and 6, but that doesn't help us. 2 and 3 are probably closer to the mark. 2 times 3 is positive 6. One of these needs to be negative. Since I take the sign of larger and I have a negative down there, the larger must be negative. So the answer here is going to be an x plus 2 and an x minus 3. I still have that x out front. That didn't go anywhere. And then I need to do another ninja star over here. This one is going to be a ninja star that says what 2 terms add up to that middle coefficient of 7 and at the same time multiply to that last constant of positive 12. Well, what are the factors of 12? 1 and 12, that doesn't help us get to 7. 2 and 6 doesn't help us get to 7. And 3 and 4 do help us get to 7. While 3 times 4 does add up or multiply to a positive 12, they don't add to a negative 7. These both need to be negative in order for this to work, which means I have an x minus 3 and an x minus 4. Again, just like in part D, I need to group together all of my common linear pairs. I had an x minus 2 and an x minus 2 for a total of 5 of these, because 1 and 4 makes 5. I have an x minus 3 and an x minus 3. I'm going to pair those together, and I'm going to say that this is really all equal to, these are all y equal to, by the way, that hasn't changed, x times, this is a bad parentheses, x times x plus 2, and parentheses times x minus 3. This entire quantity, there's 2 of those, times x minus 4. Now that we've done all the factoring, we can move on to keep solving. So let's go ahead and find the degree. The degree of this polynomial is best found by actually looking at this term up here instead of this term down here. I have an x to the power of 3. All of these are too small and won't affect us. All of these are too small and won't affect us. I'm going to multiply these 2 polynomials, which means I'm going to add up their exponents. 3 and 2 add up to a degree 5. All right, to find the zeros, I think by this time you guys have already found the trick. You just set each of these equal to 0, right? So I'm going to say x is equal to 0 is the first one. X plus 2 is equal to 0 is the second one. X minus 320 squared is equal to 0 is the third one. And am I going to run out of room? Maybe. X minus 4 is set equal to 0 is the fourth one. So this one, subtract 2, and I get x is equal to -2. If I square root, I get x minus 3 is equal to 0, and then add 3, and I get x is equal to +3. Add 4 over here, and I get x is equal to 4, and I have all 4 of my zeros. I have 0, -2, +3, and +4. Finally, I have to check what the multiplicity of each of these is. So the multiplicities are, well, this 0 came from this x, and this x was to a power of 1. I'm going to list all the powers. Power of 1, and power of 1. These are all multiplicities of 1s, and this is a multiplicity of 2. I'm just going to write those down. The multiplicity is 1. The multiplicity is 1. The multiplicity is 2. And the multiplicity is 1. Whew, a lot of work. Let's continue. Now we're going to talk about complex roots. So some polynomials have roots that contain an imaginary number. So you can see down here, eventually we get an imaginary root. This means you will not see them on the graph. This graph is reserved for real roots. Check it out. Where does this graph cross the x-axis? It doesn't. You didn't see it. You never saw any x-intercepts. Therefore, you never saw any roots, any zeros. So in this graph of f of x is equal to x squared plus 1 is shown to the right. And if we set x squared plus 1 is equal to 0, watch what happens. If I subtract 1 and subtract 1, I get this equation right here. And if I square root both sides, square root and square root, you have to do plus or minus every time you have a square root. And we get to this line down here. And the definition of the square root of -1, as we all remember, the square root of -1 is I, which means this is plus or minus I. There are two roots. You just didn't see them. One of them was positive I. One of them was negative I. All right, kind of scary that there are roots that we didn't even know about, but there they are. So this is another key understanding. So all imaginary roots come in pairs. There's always 2 imaginary roots, or 4 imaginary roots, or 6. You'll never have 1 imaginary root, or 3. You'll never have odd numbers. So all imaginary roots come in pairs, aka there's even numbers of them, right? If you have a plus bi as one root, then the other root must be a minus bi. A minus bi. That's known as a conjugate pair. Again, conjugate just means that you switch the sign from a minus to a plus, and it's a pair because there's 2 of them. 1, 2. So conjugate pairs. All right, let's dive into example 2. Determine the conjugate of the following complex numbers. Again, essentially what we have to do is we have to change the sign in front of the imaginary term. The real term does not change. It never changes. Only change the sign in front of the imaginary term. So there's the imaginary term. The sign in front of it was a positive. Therefore, the pair is negative for I. Okay, the sign in front of this I was a negative. Therefore, its pair is a positive I. All right, this is a 2 minus 3i. The sign in front of the imaginary was a minus, so it turns into a 2 plus a 3i. And the sign in front of this imaginary term was a plus. We'll switch that to a minus 2i. So this is a -4 minus 2i. All right. Let's do the fundamental theorem of algebra. This is a super duper important one in Algebra 2, and it's reviewed now in AP Precalculus. A polynomial of degree n has exactly n complex zeros. And when I use the word complex, that means a mixture of real and imaginary. If you've forgotten that, complex has 2 different parts. It has real and it has imaginary. If I look at all the reals and all the imaginary zeros, then you'll have exactly n many zeros if you have a degree n. So if I have a cubic of degree 3, we'll have 3 complex zeros when counting multiplicities. Yes, I agree with all of this. All right, so let's move down to example 3. The graph of the polynomial function is shown in the figure above. Okay, I see it up there. It is known that x equals I root 3 is a 0 of f. If f has degree n, what is the least possible value of n? All right, so we know we have 1 imaginary root, which means we have to have a second imaginary root. So we also, by implication, since they always come in pairs, we also have to have x is equal to the negative version of the imaginary number, negative I root 3. So already we are up to 2 roots, which means we're at least something with an x to the power of 2, if not higher. But if we look at the graph, we also cross the x-axis. We cross the x-axis here at x equals to 3, and because we went through that point, this is an odd power. So this one right here is something like x minus 3 to the power of 1. And that will solve, and when we solve this one, this will imply that x is equal to, I'll write this out long way though. I'll say x minus 3 is equal to 0, and therefore x is equal to 3. That gave us this x-intercept of 3. So far, so good. This one turned around. Whenever we turn around with an x-intercept, that means we have an even multiplicity, which means right here, this is something like x plus 1 to the power of 2, or power of 4, or power of 6. The problem is we're trying to find the least number, so let's choose the smallest one, power of 2. So how many, what is the power that we're looking for? So we know we had 2 here, 1 there, and 2 there. Add these all together, 2 plus 1 is 3, plus another 2 is 5. This has to be an x to the power 5. So this is something like x to the power 5 plus ... plus something else. So the least value of n has to be equal to 5. Or it could be bigger. Like, for example, this number here could have, well, it crossed pretty straight, so I don't think it's going to be 3, but it could have been 3. This could have been a 4, or it could have been a 6. There could have been more imaginary roots that we didn't know about. But again, we're doing the least number, so we're just going to do n is equal to 5. All right, so let's move on to polynomial inequalities. Let's do the reminder here. When we write f of x, we are referring to the y value. So f of x and y value, these are kind of one and the same thing, right? On the graph of f of x. That means whenever I say f of x is greater than 0, what I'm really saying that the graph of f of x is above the x-axis. And when f of x is less than 0, that means that the graph of f of x is below the x-axis. Another way of saying f of x is height. So I can cross this off here and say height. The height is above, or I can say that the height is below. All right, so consider that function. There it is. Where does f of x equal to 0? I'm going to switch this one, and instead of saying f of x, I'm going to say height. Where does the height equal 0? Well, that's where we touch the x-axis. In this case, where we cross through it. We touch the x-axis here, here, and here. Those happen at x values -3, -1, and 3. Okay, where am I having a height? This f of x, I'm going to rewrite this as height. Where do I have a height that is greater than 0? Where do I have a positive height? And I want to write this in pen. A positive height. Well, a positive height is only in these highlighted regions right here and right here. That's where we are above the x-axis. So that happens when we are between -3 and -1. And it also happens when I am greater than 3. So between, I'm just going to say 3 to infinity, or 3 to whatever value it goes to. I guess we end at 3 to 3.7. Say 3.7. Because there's no arrow to indicate that it went on forever and ever. Where is f of x? Again, change that to height. Where is the height negative? Because I'm less than or equal to 0, and I will highlight that in purple. I am a height that is negative down here and down here, and that happens between, and I'm going to write this down, between -4 and -3, and also between -1 and 3. That's all the purple region down there. Excellent. All right, so here's how we solve non-linear inequalities, how we solve those polynomials. So first of all, we set it equal to 0. Then we're going to create a sign chart with the solutions for step 1. I'll show you what a sign chart looks like down here in example 4. Then we're going to do some test values in between those values from step 1 on each interval to see if the values in the interval are positive or negative. So I'll just say they're either a positive or they're a negative. And then we're going to interpret the sign chart to answer the given inequality for the problem. Okay, and it also has this cool note down here. Be sure to write your answer in interval notation and think about endpoints. Okay, so not inequality notation, but interval notation. So what do we have down here? So step number 1, we're going to set this thing equal to 0. So set this thing, okay, because we're doing inequalities. So we're going to set this thing and pretend this is an equal to sign. Set each of these equal to 0 and see where that happens. So we are going to say x minus 3 is equal to 0. We're going to have x plus 1 is equal to 0. And we're going to have x plus 4 is equal to 0. That's step 1. And then we need to solve these so that if I add 3 both sides, this is 3. If I subtract 1, this is negative 1. If I subtract 4, x is equal to negative 4. Okay, so now I'm going to do a sign chart. So this is how I make a sign chart. I make a line, make it a straight line, and this is a line that represents all of our x values. So I'm going to plot all of these on the line. So the first one, the most negative, is negative 4. So I have negative 4, then I have negative 1, and then I have 3. Don't worry about scale here. Yes, this distance here is 4, and this distance here is 3. I don't care about the scale. So what I want to do now is, okay, I made the sign chart, and I'm going to test the value. So this is the sign chart. I'm doing test values. So I know that I am at 0 here. I'm at 0 here. I'm at 0 here. These are potential gatekeepers between, they're kind of like Hades, right? The gatekeeper to the underworld, right? I can go from positive to negative, but I have to cross through the gates of hell. I have to go through this to the underworld. I don't know if I turned around. I don't know if I went from the bottom to the top. Am I exiting from the underworld to heaven? Like, what's going on here? I need to figure that out. So the way that we do that is we plug in a random value. So I'm going to plug in a value that is more negative than negative 4. So like, let's plug in negative 5 and see what happens. When I plug in negative 5, I purposely did this in a different color, and I did a different mark to say, hey, this is a test value. This is not an actual 0. Maybe I can do a 0 here to let myself know that those are zeros. These are all zeros, and these are test points. So I'm going to make this a point. I think that's a cool way to distinguish between the two. When I plug in negative 5, I want to figure out the sign on this one, and this one, and multiply them together. I just care if it's positive or negative. When I plug in negative 5 to this x, I get negative 5 minus 3, which is a negative 8, so I just write a negative. When I plug in negative 5 to this x, I get negative 5 plus 1, which is negative 4, which is negative. And when I plug in this negative 5 to this x right here, I get negative 5 plus 4, which is, again, negative. When I multiply these three negatives, what's a negative times a negative times a negative? Well, negative times a negative is a positive, and a positive times a negative is a negative, which means we will write on our sign chart over here, this is a negative. I'll write that above. Okay, then we do the same thing. I'm going to erase this. And then we do the same thing again for a new test point. Find a test point in between negative 1 and negative 4. Let's choose like negative 2. I want to write this in pen. Negative 2. When I plug in negative 2, I'm going to get a negative here. I want a negative here. I get a negative here, and I get a positive here. This one switched signs because this got the positive 4 overrode the negative 2. So a negative times a negative is a positive times a positive. This is now a positive on this entire interval. And I will remind you, you have to be positive because you are not allowed to go through the gates of hell. You're not allowed to go through this gatekeeper and switch to a negative. You have to be only positive between negative 4 and negative 1. All right, I want to do a test value in between negative 1 and 3. I really like the value of 0, and that should be a filled-in point. So when I plug in 0, let's go ahead and erase these signs up here. When I plug in 0, I'm going to get a negative, a positive, and a positive. If I multiply these together, a negative times a positive is a negative, and a negative times a positive is a negative, so this is still a negative. And finally, you're going to plug in another value over here. What's a number bigger than 3? Let's plug in 4. When I plug in 4, let's erase these again and do it again. When I plug in 4, I'm going to get positive. Plug in 4, I get positive. Plug in 4, I get positive. All of these multiplied together gives you a positive. So again, we are almost done. We have now done test value. We've now done step number 3. We're now doing step number 4. We're going to interpret this sign chart. So we were asked, where is this function greater than 0? We're greater than 0 when we're positive. So we're greater than 0 between negative 4 and negative 1. And we're greater than 0 when we're greater than 4. So I'm going to say this. We're greater, so our answer is going to be here in red. Between negative 4 and negative 1. And also whenever we're greater than 4. So 4 to infinity. Done and done. All right, we're doing example 5. Kind of the same exact thing. Same steps. Set them each equal to 0. So I'm going to say x plus 2, that quantity squared is going to be set equal to 0, and this x minus 5 is going to be set equal to 0. Square root both sides here, square root, and I'm going to get x plus 2 is equal to 0. Then subtract 2, and I get x is equal to negative 2. Over here, add 5, and x is equal to positive 5. So I only have 2 zeros, 2 potential gatekeepers on my sign chart. So on the sign chart, I'm going to do a 0 here, a 0 at negative 2, and I have a 0 here at positive 5. Okay, let's go ahead and do some test values. I'm going to do a test value right here. Let's plug in negative 3. When I plug in negative 3, it doesn't matter what I plug into this value because it's squared. It's always, always, always going to be positive. It doesn't matter what point you plug in. But if I plug in negative 3 to this value over here, negative 3 minus 5 will be negative. A positive times a negative is a negative. Okay, let's do a new test point. Let's choose 0 in between -2 and 5. It doesn't matter. Any point will do. When I plug in 0, this is always positive. I can kind of ignore that one. But when I plug in 0 over here, I'm going to get 0 minus 5, which is also a negative, which means I haven't changed. I'm still a negative. And I want to kind of think about this just for a sec. I was negative. I went to the gatekeeper, and I didn't go to the underworld. Maybe I saw the lights, and I decided, nope, I'm going to keep living. I came back up here. I didn't go to the underworld. I'm still, well, I guess I'm trapped in the underworld, aren't I? I'm still negative, and I'm still negative. I wasn't let out of the underworld. I'm still negative. I'm still negative. All right, and then maybe we'll switch signs. Maybe we'll go to positive over here. Let's test. So let's go ahead and erase this one. I'm not going to erase our sign over here. That's always positive. Let's do a test point of, 6. When I plug in 6 into our x value right here, I'm going to get 6 minus 5, which is positive. A positive times a positive is a positive, and I can erase those all again. And I have my sign chart. So now we need to interpret the sign chart. We were asked, where are we less than or equal to 0? So it's including these gatekeepers. Well, I'm less than or equal to 0 everywhere right here. I'm equal to 0 there, I'm equal to 0 there, and I'm equal to 0 here, I'm equal to 0 here, and I'm also below here. So it's everything to the left of 5. So everything to the left of 5, the way that we write that is you say between negative infinity and, that was a terrible 5, and 5. Oh, I made a mistake. I said right here that this is not equal to 5, but it is equal to 5. We are equal to 0 at 5, so I need to change this parenthesis into a square bracket. Now we are technically correct. All right. Moving on. We are determining the degree of a polynomial given a table of values. How do you do these types of problems? All right, so let's read here. If given a table of values with equal width input intervals, we can determine the degree of a polynomial by examining successive differences in the output values. We're looking at, for example, the first difference, the second difference, et cetera, et cetera. The number of successive differences needed for the differences to be constant is equal to the degree n of the polynomial. If all of the third differences are the same, it's a degree 3. If all the fourth differences are the same, it's a degree 4. If all the fifth differences are the same, it's a degree 5. That's what it's trying to say here. So determine the degree of the polynomials represented in the tables below. All right, let's try this guy. We're only allowed to look at differences, by the way, if these are all constant changes. Over here, this was a +2, +2, +2, +2. We have permission to look at the differences. So this first column is going to be called the first difference column. So how much do we change to get from -2 to 3? We add 1. How much do we change to get from -3 to 1 to -1? Sorry, we add 2. How do you get from -1 to 4? We add 5. How do you get from 4 to 12? We add 8. That was the first difference. If all of these were the same, it would be a degree 1 polynomial, but it is not the same. So we're going to go ahead and look at the next column, which is the second difference column. All right, how do I get from 1 to 2? I add 1. How do I get from 2 to 5? I add 3. How do I get from 5 to 8? I add 3. I'm worried that I've made a mistake, and I have indeed made a mistake. Okay, I don't know if you guys caught that, but I said to get from -2 to 3, I add 1. I shouldn't add 1. I should subtract 1. I should subtract 1. And again, still, these are not the same, so it's not a degree 1. But that does change this number over here. How do I get from -1 to 2? I have to add 3. Add 3. Okay, hey, check it out. All of the second differences are the same. If the second differences are the same, this is a degree 2 polynomial. All right, let's do part B. Are we allowed to look at first, second, third differences, etc.? Do +3, +3, +3, +3. Because all of these are constantly increasing by the same number, it's a constant increase, we are allowed to look at first, second, and third differences, and fourth and fifth, etc., etc. So let's look at the first differences. First differences. How do I get from -2 to 0? I add 2. How do I get from 0 to 10? Holy moly, I add 10. That's a big increase. I add 17. I add 23. My goodness. Okay, that was the first difference column. Obviously, these are not the same, so it's not a degree 1 polynomial. Let's look at the second difference column. How do I get from 2 to 10? I add 8. How do I get from 10 to 17? I add 7. How do I get from 17 to 23? I add 6. Again, these are not the same, so it's not a degree 2 polynomial. Let's try it for a third difference. Let's call this the third difference. How do I get from 8 to 7? I go down 1. How do I get from 7 to 6? I go down 1. Hey, check it out. All of these numbers are the same. Therefore, this is a degree 3 polynomial for the third difference column that is all the same. This is a degree 3 polynomial. All right, and I can be maybe more specific in my notes. I'll say because third difference is constant. And then over here, I'll say degree 2. Why? Because second difference is constant. AKA, it doesn't change. It's always the same number. All right. Then we're moving on to this even and odd functions, and then you guys can finally be released to the worksheet. Let's see what we got here. Even function. An even function is symmetric over the y-axis, which means negative values of x and positive values of x. It doesn't matter if I go to -2 or +2, they have the same height. Again, f of x represents height. If I go to +2 and -2, they have the same height of -3. If I go to 1 and -1, they have the same height here. And an odd function is symmetric about the origin, which means if I have a value right here, it rotates around here, around the origin, and we see that it is indeed on the other side. So it's kind of like reflecting over the y-axis and the x-axis. So if I reflect over the y-axis, we come over here, and if I reflect over the x-axis, I come over here. So it's kind of like a double reflection for an odd function. And they gave you examples of them down here. This is an even function because, check it out, the degree here, I'll write it down here, the degree here is 4. And because that's an even degree, we have an even function. Over here, we have a degree 3. Because the degree is odd, this function is also odd. All right, nice to know. Example 7, determine if the following polynomials are odd, even, or neither. Okay, well, I can just look at that number. Oh, I cannot look at that number, can I? I am a liar. I totally misspoke up here. That is like, it sometimes is true, but it's not always true. Please, oh, I wish I could edit that out. I am a liar. Please ignore that. Because right here, because I was assuming that we had no like middle term. If you do have a middle term, you aren't sure. What we have to do is we have to check to see if the terms on the left and the right are equal to one another. So, I don't know, let's plug in 1 and -1 and see if we have the same height here, right? Let's plug in h of 1 and see if we have the same height as h of -1. So when I plug in 1, I get 2 times 1 to the power 4 minus 1 squared plus 5, which is going to be 2 minus 1 plus 5, which is going to be 6. All right, if this height is the same height down here as h of -1, then it's going to be even. And if it's not, then it might be odd. I don't know. We'll have to do further analysis. Let's do 2 times -1 to the power 4 minus 1, -1 to the power of 2 plus 5. This is going to be equal to 2 minus 1 plus 5. Again, whenever you have an even number, these signs turn positive, and this is going to be equal to 6. Hey, okay, because these are the same heights on either side, -1 and +1, of the origin, of the y-axis, this one is even. Whew. All right, if I suddenly had like a minus x to the power of 3, it would not have been even. It would have been neither. All right, what about this one? I have a feeling it's going to be odd just because I have an odd and an odd here, but let's go ahead and check it. So let's just plug in 1 and -1 and see what happens. So k of 1, I'm going to get 1 cubed plus 3 times 1 minus 1, and that's going to be equal to 1 plus 3 minus 1, which is equal to 3. Okay, what happens if I plug in k of -1? Okay, there's one of 3 things can happen. The first thing that can happen is I get a value of 3, and the answer is they're even. The other thing that can happen is I get a height of -3, which means it's odd. And the other thing that can happen is it's not any of those 2 values, which means it's neither. Let's go ahead and see which one it is going to be. Okay, so I have a -1 and quantity cubed plus 3 times -1 minus 1, which is equal to -1 minus 3 minus 1. And that's going to be equal to -5. I thought it was going to be odd because this one was odd and this one was odd, but this one would have to be a +3, or sorry, a -3, while this one was a +3. These need to be opposites of each other, but it's not. So this one is actually neither. All right, what about C? We'll check it out. If I look at this point right here and this point right here, this point right here, those heights are opposite of each other. One is -3, one is +3, and it's symmetric over that line y equals x. If I reflect this point over and this point over again, a double reflection is odd. This is the definition of an odd function. And you can just look at the height there. You can say that the height of -1 is equal to the height of, well, say the height of -1 is 3, and the height of +1 is -3. Because these two heights are opposites of each other, aka just multiplied by -1, that is the definition of odd. D is neither. I can just look at it. And I mean, you might think, but Mr. Sindel, look, it's symmetric over this line. Well, it's not this line through the vertex that matters. It's the line of the y-axis. This height right here has to be this height right here, and it's not. So, and I can just plug in, right? Watch this. If I do, what is the height at -1? The height at -1 is 1, and it's this point right here. What about the height of +1? The height of +1 is down here. That's -3. These are not even anywhere close to each other, so that's why it's neither. Cool. That was the rest of the notes. Yeah, the next thing that we have is a worksheet. So that completes the notes for AP Pre-Calculus, topic 1.5, polynomial functions and complex zeros. It was a long one. Thanks for watching.